This video is part 2 of the video series on automating the Accu-Slice system. In part 1 of this video series, we described the general operation of the system, the various components we use to assemble the system, and I briefly showed how it works to cut boards on the bandsaw. In this part 2 of the video series, we'll be describing some additions to the system, including limit stops on both ends of the system and a new electronics console to operate the system. I'll also be describing in some detail the software and the actual programming steps I use to make the system operate properly. The first thing I added to the system were limit switches. And these are switches on both ends of the ball screw. And these work by when the support for this carriage comes down and hits this switch, it closes the switch and that shuts down the system. So if you're running, and as soon as that system hits the switch, it shuts it down and doesn't damage the system. Without those systems in place, the system could crash and just bomb out the motor and crash the motor. So those are done by making brackets. I have 2 brackets that mounted on both of the supports for the ball screw, and the switch is located just underneath this support. These pieces are machined on my little mini mill, and they're positioned to accurately position the stop so it accurately hits the mechanism here. I will probably replace these with some Hall sensors in the future. I have them in order. When they come in, I'll put them on and give them a try, but they might be better than these contact switches. So I'll start the automated system running. The carriage is moving, it's just about ready to hit the contact switch, and it stops the system. When I installed this limit switch on the end of the rail, the wires for this limit switch have to go all the way back to the other end of the wire. And I didn't want those wires hanging all over the place and getting tangled up and getting tangled up in the screw system. So what I did is I ran them through the channel on the rail on the Accu-Slice system. Of course the wires lay in the rail, but they can still loose around and fly out. So I did, after I put the wires in there, I put the strip of wood. This is a strip of thin veneer that I cut on the Accu-Slice system. And this just slides in the rail and covers up the wires so they can't come out. So this is the actual strip that I put in. And you can see the wire in there. And it just covers the wire up so it can't get tangled up and interfere with the system. The next thing I made was this new electronics console. If you remember from the prototype, we used a breadboard and the switch here with a bunch of wires on it, and I had some little small switches here, which were very hard to push because there's so many wires in place, and they're very small. So I made this console, which is much bigger, has some bigger buttons, gives you a lot more room. Everything electronic-wise is enclosed in this case, and it's a nicer system to operate the system, just nicer and cleaner. So let me take this cover off the assembly here, and I'll show you what's assembled inside. This is a complete electronics console, and in this console I have all my electronics, which is a very, very tight fit, but it all does fit. I have a 6.5 amp 24 volt DC power supply. I have my Arduino board. I do have a breadboard here for attaching some wires. And this is a stepper online model DM542T driver for the stepper motor. And this is a 4 amp driver for the motor, because I do have a 4 amp stepper motor on the system. So everything's contained in this case with this front panel, which I put all the various switches in my stop position, left, right, and then jog positions, and a potentiometer to adjust the speed. So everything's on there, nice and easy to see and adjust. And this is not complete. I will be putting plugs on the back so I can unplug things to move it. Right now everything's hardwired in, but I will put some plugs on the back so I can disassemble the system to move it and reattach systems. Let me put this back together. To go left, I just press the left button. I can adjust the speed, up and down, stop it. To go to the right, press that button, stop it. And these jog buttons are used to set the position. Like when you're first setting up your system, you want to get it exactly set, and you don't want to have to stop this and guess when to stop it. So these buttons only run the system when you hold the button down. And it stops right away. So these are good. They're called jog buttons, and they're used to do fine tuning on your system to get it aligned properly for your operation. This potentiometer, I said adjust the speed. I go all the way from actually 0, but normally the smallest is around 5 inches per minute, up to 150 inches per minute. Next, I do have this electronics console hooked up through the serial port to the laptop PC. Originally was planning on having a digital display here to display the speed of the carriage to the bandsaw blade. And I actually bought some, they're called OLED displays, and they work quite nicely. And I spent a whole day getting it programmed, getting it set up, and getting it working. But when I put it on the machine, it affected the speed of the stepper motor. It kept getting jumps in the stepper motor. And it turns out this Arduino, when you try and doing two things simultaneously, one interferes with the other. And the digital displays actually take a lot of time, and as a result they delay the steps in the stepper motor. And I spent quite a while programming this, trying to put in different steps of the program to make it work, and I just couldn't get it to work. And then when I checked online, found other people tried the same thing, and it doesn't work. But I won't give up on that. I'll keep trying. Another possibility is getting 2 of the Arduino modules and hooking them up in series and see if that works, but I'll work on that in the future. But I also want to put some other switches up here when I add the wide travel for the Accu-Slice system. So I'm using the PC, and actually the PC does display the speed in inches per minute. So I have a screen that shows up here, and it shows the actual speed as I'm jogging. I can change the speed and it'll show up on the screen. I'll show you that in a minute. So this is a screen that displays as I'm running the system. There are 2 sets of numbers on the screen. The number on the left is the actual speed in the computer that it runs the system. And the number on the right is a calculated speed that I calculated based on the carriage running through the bandsaw blade. And that's the actual speed of the carriage running through the bandsaw blade in inches per minute. So when I start the system, I can start at a low speed, and as I increase the speed, it displays, as I said, the actual speed of the carriage through the bandsaw blade. So let me start it. Start it slow. And as I increase the speed, the number increases. And it goes up to 150 inches per minute. And slow it down. See, the number is positive. When I reverse it, going the other direction, it shows the same number, shows the speed in the reverse direction. So I originally was hoping to have a digital display to put on here to show the speed of the carriage to the bandsaw blade in inches per minute, but that didn't work because of the speed of the OLED displays. Turns out those OLED displays are bitmaps. They're not data, and as a result, that bitmap takes a lot more time to produce, and that's why it interferes with the stepper motor. But in reality, this is probably a better system anyway, because I can only display the speed of the carriage to the bandsaw blade, but I'll be able to manually put data in here to control the system. So I'll be able to control, the Y position of the index wheel. So I can put data in here. If I want to cut a board 100,000 inch thick, I can type in 100,000. If I want it 25,000, I can type in 25,000. So all that data can be manually put in here, sent to the system, and then you can run it. So next I'll go to the main computer where I did the programming for this, and I'll show the actual program and the steps that were used to produce this, how it works, and show exactly what was done to modify the system to make it work like I'm using it. These are the components we're using for this project. Starting with the Arduino Uno board in the center, the 4.2 amp stepping driver, the 4 amp bipolar stepping motor, a 24 volt 6.5 amp power supply, a potentiometer, and a series of input pull-up switches. These switches are all input pull-up switches, which means they don't need the 10K resistor in the circuit. These first three momentary switches operate the stepper motor to advance the Accu-Slice carriage, either going to the left, to the right, or stopping it. These next two switches are the jog buttons. By pushing these buttons down, you advance the carriage to the left or right, but the carriage only moves when you press the button down. They're quite useful in setting up the system. These last two switches are the limit switches, which stop the carriage from running when it reaches the end of the rail. On the Arduino board, pins 2, 3, and 4 are for the three main running switches. Pins 6 and 7 are the step and direction inputs to the stepper driver. Pins 9 and 10 are the limit switches, and pins 11 and 12 are for jogging the stepper motor. The potentiometer, which controls the speed of the stepper motor, is connected to the AO analog input. Now let's look at the Arduino software code or sketch for the operation of the automated Accu-Slice system. This is an ongoing project, and the software will be heavily modified in the future as I do some additional testing and add additional new features to the program. The main software code for the operation of the stepper motor, the forward and reverse operation of the stepper motor, and the stopping of the stepper motor was obtained from the EasyDriver example web page, example number 5. This was a starting point for the development of the program for our system. I then edited this program to fit our system and added the new features such as the jogging feature and the limit switches. This program uses the ACIL stepper library. This library was selected due to its ability to operate multiple stepper motors, which will be required in the future. We first defined the three input pull-up switches for the operation of the stepper motor, pins 2, 3, and 4. The jog switches were defined at pins 11 and 12, and the limit switches were defined for pins 9 and 10. All of these momentary switches are input pull-up parameters, which do not require an external resistor in the circuit. Instead, they use the internal resistors available on the Arduino digital pins. The potentiometer, which controls the speed, was defined as analog input AO. The maximum speed of the stepper motor was 6,000 steps per second. This will equate to 150 inches per minute for the operation of the Accu-Slice system. This value is the floating feed rate listed at the end of the section of the sketch. This was calculated by dividing the program current speed, which is number of steps per second, by 40. This provides for the actual feed rate of the Accu-Slice carriage in inches per minute. This value will later be displayed on the PC screen. This next screen is the setup screen, which further defines the 7 input pull-up switches. This final screen is a complete program listing for the loop run. I did shorten this section of the program so that the entire section would display on a single screen. I did this by eliminating the section spaces, which does make it harder to read. This was done only for display purposes. This code includes the original code of the program and the code I added for the limit switches and also for the jog switches. I also added the serial print section to print both the speed of the stepper motor in steps per second and my calculated value of the actual speed of my carriage in inches per minute. These values will be displayed on our Arduino screen for viewing. As I mentioned earlier, I did try to add an OLED digital display screen for the system to display the speed. I tried 2 different screen designs which used different libraries and software routines, but neither one worked. However, after spending a good deal of time trying to make it work, I did an internet search and discovered that others had also tried this and had the same problem. An answer may be using 2 Arduinos, which I may try in the future. The software is still in development, and there are many changes to be made going forward. If anyone has any suggestions for improvement, I am open to your input. This concludes part 2 of this video series on the automation of the Accu-Slice system. In this video we described our electronics console and our limit switches which are added to the system, and we also briefly described the software which is still in development. Part 3 of this video series will be coming shortly. In this next video I'll be looking at cutting some actual boards on the system. I'll be starting out by cutting a board probably 1.5 inches, 2 inches tall, and cutting at different speeds to the bandsaw blade. I want to see how speed affects the surface finish on the boards. I'll also be looking at parallelism of the boards that are being cut on the system. I have added additional weight to the left side of the rail more than on the right side, and if this rail gets skewed in the process, I'll get different thicknesses from one end of the board to the other, so I'll be checking that out. After that, I'll be doing a study on cutting different thicknesses of boards to the bandsaw. Starting off with, I said, an 1.5" board, maybe going to a 3" board, and maybe even up to a 12" board, to see if the system has enough power to push that board through the bandsaw blade. If it doesn't have enough power, the entire system may be redesigned. Putting a bigger motor on here will create a bunch of issues. This is a NEMA 23 motor. The NEMA 32 is probably 4 times heavier and adds a lot of weight to this left side of the table. That may be a requirement for redesigning the entire system. So I'll be looking at that if that's required. Hopefully it's not, but we'll see how it works out. After that, in the future, we'll be looking at how we can automate the Y mechanism, but that's a future video. After everything checks out, we'll see if it's doable. This is a continuing project to develop an automated Accu-Slice system. If you have any suggestions or concerns or comments, I'd like to hear from you. I'm always looking for a better way to do things, or maybe new features need to be added to make the system more usable. And once again, thank you for watching this video.